Hi, welcome back to my series on converting this 1978 bus to all electric. In this video, I'm going to talk about how I'm going to build the battery pack that'll go in this bus. But more importantly, if you're planning on building an EV, I'm going to give you the tips and concepts on how I'm going to build my battery pack, both in terms of what the chemistry of batteries I'm going to select and where to buy the batteries and how to arrange the batteries in order to achieve the goals that I've set out in terms of what I want for this car's acceleration, range, and cost. So stick around and you might learn something. Okay, so let's get some basic theory out of the way just to start out with. Electric motors like the one in my van require power to turn it. And as you know, power is measured in watts, which is simply voltage multiplied by current. So back in the day for electric vehicles, you made a motor spin faster by adding voltage to it. Early implementations of electric cars had a series of lead-acid batteries and simple circuits with contactors that would add a battery in series to increase the voltage, which made the car go faster. The problem is it was really jerky and not a good experience. So modern motor controllers like the one I have use a constant voltage and they just pulse the high current to the motor, and that's how it controls the speed. So deciding on the voltage of our battery pack is the first thing we want to do here. And the voltage that we decide on really depends on what your motor controller is capable of. So my warp drive controller that I've shown you before is rated at 160 volts nominal. But if you read the manual, it really can handle up to 180 volts nominal. If I upgrade it, like I've mentioned many times, to the NetGains Hyperdrive AC setup, that one's rated at 144 volts, but if you read the documentation, it can go up to 180 volts nominal. In both cases, they probably have components internally that are rated at about 200 volts. My Chevy Volt, which is a production OEM car, has a motor controller capable of handling 350 volts. And Tesla drive units can handle between 400 and 500 volts depending on what version they are. And some EV manufacturers are even making drivetrains capable of 600 volts. Now, speaking of the volt, I'm going to show you a quick video clip of some typical acceleration. And what I want you to do is watch what happens in that power meter on the dashboard there. As you can see, average acceleration in that car requires about 30 to 50 kilowatts of power. Heavy acceleration, maybe 70, 80, 90 kilowatts of power. Now with 350 volts, I can push 35,000 watts or 35 kilowatts to that motor using only 100 amps. Because again, it's 350 divided by 35,000, that's 100 amps. If my system voltage was half of that, like in the terms of my EV here, I would need 200 amps from the batteries to achieve that same acceleration. So the reason that OEMs are going with much more higher voltage systems is for several reasons, but to start here, you can see it's so that we can have less current to achieve the same kilowatts of output to the motor. What that also means is with less current needed to deliver to the motor means your wiring can be smaller and there's less strain on the batteries in terms of current draw and heat. So there's a lot of advantages to going up and up and up in voltage, which is why OEMs are much more higher voltage. The downside of going higher up in voltage is the components internally in the controllers need to be redesigned, because the higher voltage you have means different design in terms of insulation and the quality of components in there, which means it's a higher cost, which is probably why a lot of the off-the-shelf EV parts for the aftermarket builds like mine are much lower voltage. Okay, let's talk about batteries. The typical batteries that we have available to us nowadays are all based on a lithium chemistry. So it started with like lithium ion and then went to the lithium iron phosphate, or LFP. But then nowadays there's like 5 other newer type of lithium chemistries. Like, for example, lithium cobalt oxide, or LCO. Lithium manganese oxide, LMO, lithium nickel manganese cobalt oxide, or NMC, lithium nickel cobalt aluminum oxide, or NCA, and I believe that's the one that Tesla is currently using a lot of, and then lithium titranite, if I'm saying that right, or LTO. So a lot of different lithium chemistries are out there now, and they all vary in really two different terms. The nominal voltage that each cell has, like in the example of the lithium iron phosphate, typically run about 3.2 volts nominal, where the older lithium ion and some of the newer lithium chemistries here can do 3.6 or 3.7 volts nominal. And the other big thing is the different energy densities, meaning how much capacity can you have versus how the size and weight of the actual physical battery. So I have an array here of a few different batteries that I've kind of acquired. This is actually just lithium ion batteries, and this was what, like, the Tesla Model S, the older style Tesla cells, this is what they were made of. These happen to be 18650s, and they're cylindrical lithium ion cells. This is basically the size of a AA battery. And newer designed Tesla cells are in different formats that are like more like C or D cell sized batteries, and so they have they're made of newer lithium chemistries, and they're a little bit larger and more optimized for energy density. But this is kind of what I was originally thinking about building my pack. Much like a Tesla Model S pack, I was going to kind of make my own out of a bunch of these cells. And then you would typically take nickel strip like this and put it across the top here and spot weld all these together. Well, here's the problem with this, and this is why I abandoned it. It's just a lot of work, right? To spot weld all of thousands of these cells together in series and parallel configurations to make the pack that I want. It's probably the cheapest option, but as I'm looking at the amount of work and the tedious effort required, I abandoned that. So another option might be to buy a Tesla Model S module, which has all these batteries, the thousands of these cells, already spot welded and built into a nice production quality module. The downside there is that those things typically cost between $700 to $1,100 a piece, but you get the advantage of it already being done for you. So I abandoned that. Now what I did with in my previous build was I used these cells right here. This is a LFP, or lithium iron phosphate module here, and this is in the format called prismatic. And what prismatic means is typically in the lithium iron phosphate are pouch cells, like what's in a laptop. That's what makes, starting in, like, I don't know, 2011 with the MacBook Airs, that's what they started using in laptops more so than these type of batteries, because pouch cells can be real thin, and you can, make your tablets and laptops much thinner. So this is probably 5 or so pouch cells all welded together and boxed into this plastic casing with just these two terminals that you can screw into. So that's what we call a prismatic battery. The nice thing about these is it's all sort of contained. It's easy to band it together, and it's a fairly easy implementation. This is the newer version of that, and when I show you some of the sites that I buy, that I've experienced looking for batteries and buying them, they still make this version right here, which is the gray version of the CALB, which is Chinese Aviation something. They're from China. But this is a 100 amp hour, 3.2 volt lithium iron phosphate prismatic module. And then we have this big dog here, which is what I am going to put in the bus, and I'll explain this later. But this is the same as this. It's lithium iron phosphate pouch cells, but instead of just like 5 or 10 or however many are in here to make a 100 amp hour 3.2 volt cell, this is pre-configured in series and parallel configurations to do 60 amp hours at about 85 volts. So what this has is about 70 some pouch cells all in it. So it weighs 100 pounds, so it's pretty big and heavy. And it has 3 parallel pouch cells, 20 amp hour pouch cells to make a 60 amp hour 3.2 volt cell, and then 26 of those in series to make the voltage. So these are some different examples of things that I bought, but let me show you a few of the sites that I shopped on in order to find the deals that I was looking for to build a battery pack for this bus. The three I'll flash up on the screen here are batteryhookup.com, jag35.com, and greentechauto.com. Let's start with batteryhookup.com. I'm going to take you to Battery Hookup to show you the latest version of a CALB cell. It's a little bit higher amp hour capacity. It's a 3.2 volt, 180 amp hour, just like this one, only a little bit bigger. So let's talk about battery specs, because as we're looking at these websites to look at these batteries, let's talk about some terminology and specs that we need to understand how we're going to build the type of battery pack that we need for our car. So one thing you're going to see is that whole nominal voltage, right? What does nominal mean? Well, you might think of it in terms of average voltage. I think more specifically, the nominal voltage is understand how these lithium batteries typically work, right? Let's say I have a car with a 100 amp hour lithium iron phosphate pack. Each of the cells is 3.2 volts, right? You'll typically see specs like nominal voltage is 3.2, charging voltage is 3.6 or 3.65 or something like that, and then a minimal voltage is 2.5. So the battery range per cell for a module would be somewhere between 2.5 volts and 3.4 volts when it's fully 100% charged. But it doesn't discharge in a linear way, meaning like we have, what is that, 2.5 to say, well, let's just round it up to 3.5 volts. You have basically a 1 volt range per cell for that car. And let's say that 100 amp hour battery pack gives you a range of like 50 miles. You would think that somewhere between that 1 volt range, between 3.5 and 2.5, you would get 5 miles per tenth of a volt? But it doesn't work that way. What it typically does is you'll start out at 3.4 volts at the very top, and you'll drain that down very quickly. Say that first 5 miles, you'll go down 0.2 of a volt. And what then happens is once you get to the nominal voltage of 3.2, it'll kind of stay at 3.2 for a wide range, like somewhere down to like under 40%. So that's the nominal voltage range, and that's really what we're looking at when we're speccing out our battery power, because our controller and everything is rated at that nominal. You'll also see that AH rating. Amp hours refers to the capacity of the battery in terms of how many amps the battery can deliver for 1 hour. That's an important spec not only for our capacity, like how much range can we get out of these batteries, but also for how much current can we draw from these batteries in some way. So now the other big rating there is, notice on this cell, it'll have specs like max continuous discharge amperage, or max continuous charge amperage, or 3-minute discharge, or 10-second discharge amperage. And notice that the number next to it has a C next to it, like 1C, 3C, 5C, you might see 10C. What that rating is, it's called a C rating. So the continuous discharge rating, what that tells us is we can pull 180 amps out of that cell continuously without hurting it. 1C means that it's a multiplier by the amp hour capacity. So 1C is 1 times 180 amp hours, which means 180 amps. So at a 3-minute discharge, if it can handle 2C, that means you can do 360 amps for up to 3 minutes before you hurt the battery. That C rating is very important, because if we want to have a goal of our car being able to accelerate at maybe a rate similar to what my Volt can do, I'm kind of putting a kilowatt target on what my motor might have to consume for me to get a decent acceleration. Now you saw on my Volt that 70 kilowatts can do a pretty good, nice pickup, good amount of get-go there. But my bus is going to be much less aerodynamic and efficient with that power. So I'm thinking I might need to accommodate 100 kilowatts into my motor so that I can get a decent acceleration out of it. If I'm looking at how much amps I need to get out of my battery pack in order to achieve that 100 kilowatts of power into the motor to give me that decent acceleration, I take 100,000 or 100 kilowatts and divide it by the nominal voltage that I'm targeting, say around 160, and that number, 100,000 divided by 160 is a little over 600. So let's say we need 600 amps of output to get that good 100 kilowatt acceleration. Now, does that mean I have to build a battery pack with 600 amps continuous C rating? No, not necessarily. I could probably target, I don't think I'm like the 10-second discharge, which is 3C, which will be what, 540 amps. That would get me close there. I'm not real comfortable with using that 10-second because, you know, maybe I do need that for more than 10 seconds, but 3 minutes would be more than enough. So this battery pack might be a little bit weak in terms of if I put one series string together at 160 volts with these particular modules right here, would give me a 3-minute discharge of 2C or about 360 amps. It wouldn't give me quite that 100 kilowatts of acceleration that I would desire there. So that's a key spec of what we want in our battery pack in terms of acceleration. Okay, so in terms of capacity, I've just sort of been reading about different people who have converted buses and similar types of cars with similar types of motor and controller arrangements, and I've kind of derived a guesstimate on what I would need for range. What I'm targeting for my range is about 30 kilowatt hours. 30 kilowatt battery pack, if I built it at about 160 volts, I divide 30,000 divided by 160, and that's the amp hours I would need for the whole pack. That number comes out to about, what, 187, I think. I did the math. So let's just say about 180 amp hours. So if I built a single string of those CALB 180 amp hour modules, that would give me pretty close to a 30 kilowatt pack. Maybe I can go a little bit higher on the voltage since I have a little more. Maybe at 170 volts at 180 amp hours, that gives me right there about my 30 kilowatt pack. So that's a good target range. So these cells would do well in terms of if I bought, let's say, a little over so 50 of these 3.2 volt cells would be 160 volts, and add a couple more there. Let's say I bought like 55 of them to stay under 180 volts nominal. So 55 of them would give me the range that I'm expecting. The only problem would be the acceleration. I might be a little bit limited in the acceleration with a single string of these batteries. Okay, so what does that mean? Does that mean you have to look for cells that are exactly the right amp hour range for your needs? No, not necessarily. Let's talk a little bit about configuration of cells. A lot of you already know what series and parallel means, but real quickly for those that aren't initiated, I'll give you a quick rundown. When you arrange batteries in series, you're chaining your batteries together, negative, positive, positive, negative, and then at the ends of that chain, you have a negative and a positive that you would tap off of. When you do series configuration, again, you have the voltage and your amp hour rating of each of these batteries. When you put them in series, the voltage adds up, but the amp hours or the current capacity stays the same. So if I was to put 50 of those CALB 180 amp hour batteries in a series configuration, that would give me 160 volts still at 180 amp hours. Now, parallel configuration, on the other hand, is when we wire all of our positives together and all of our negatives together. When you arrange your batteries in parallel, it's the inverse of the series. Your voltage stays the same, but your capacity goes up. So if I was to just pair two of these cells in parallel together, I would still have a 3.2 volts battery, but I would now have a 360 amp hour capacity for that. Okay, so now we understand series versus parallel. There's another vernacular that a lot of people that are in the solar industry or RC car industry or EV, whatever, they all understand this, is you'll typically see a vernacular like, this pack is a 26S 3P. In fact, that's what this one says on its specs. This module right here is 26S 3P. What does that mean? Well, as you can imagine, the S is series, the P is parallel. So what they're saying there, 26 of these cells in series and 3 in parallel. And what I like to think of it as, you could do either series first and then parallel, or parallel first and then series. So for an example here, let's go to another prismatic lithium iron phosphate battery on battery hookup. This is a cell here that is still a lithium iron phosphate, but it actually has a 74 amp hour capacity. In that case, if I was to put 50 in series, I would have a 160 volt pack at 74 amp hours. Well, but these batteries cost half as much. So what we could do is buy 100 of them. There's two different ways we can arrange them to get the 160 volt pack that we need for our motor controller. We can arrange them in a 2P50S pack, whereby we take two of them, parallelize them, so you have a 3.2 volt 150 amp hour battery, and then you take those 50 of those pairs and put those in series to make your 160 volt pack. So in the end, we have a 160 volt 150 amp hour pack. Or we could put them in a single string, a series string, so 50 in a series string and another 50 in a series string, each one individually being 160 volts at 74 amp hours, and then parallel those two strings together to get the same outcome. Well, let me introduce one more concept and one more cost that we're going to have to buy when we put together this lithium battery pack, and that is, we will probably need a battery management system to monitor the batteries and to help balance them as they charge. BMS is an expense, right? These can cost $1,000. Well, the way the BMS works is you tap off each of the lowest level of cells, and that's what your BMS is monitoring, both for discharging to make sure they don't go too low, or seeing if there's an issue with a cell, or in the charging to shunt the voltage if it's charging faster than some of the other cells. But your BMS is only as good as the lowest common denominator, or your highest precision of cells. In the case of, we did a 2P50S pack, those two parallel cells become the lowest level that you can monitor with your BMS. So if I put these two cells together in parallel, positive, positive, negative, negative, and my BMS is measuring this as the lowest level cell group, if anything goes wrong with this cell group, the BMS will let me know this is the cell group that's a problem. But is it this one, or is it this one, or is it a pouch inside of here? I don't know. I pretty much have to pull both of these out and either replace them or figure out which one's the problem. So by parallelizing first, you get less precision in your BMS monitoring and charging. In the case that you do a 50S 2P, meaning you put two high voltage strings together and then parallelize those, there's a big problem with that, which is why I would suggest doing the former rather than this one. Your BMS can still measure all 100 cells individually, so you get more precision in your BMS. But the problem is, if there's any voltage differential between those two high voltage packs, which are likely to be when you put two different sets of 50 cells together, right? If, let's say, there's 0.2 of a volt difference, the moment I join those packs in parallel, a current's going to immediately flow from the higher voltage pack to the lower voltage one, because it has to kind of balance itself. That current could be substantial at 160 or 180 volts. If I was a couple tenths of a volt off and I put that final bus bar on and I'm not wearing gloves, I could have 100 amps all of a sudden travel through that bus bar the moment I connect it together. So there's a little bit of danger in connecting high voltage packs, seriesing them, and then parallelizing those large voltage series packs. So that's why I recommend the former, even though you get less precision in your BMS. So again, looking at this 74 amp hour cell and thinking in terms of how would that meet our needs, both in terms of acceleration or capacity. Now we're kind of getting into price here. On these, they have a little bit higher C rating. Now they don't tell you a C rating. What they do say is that it has 180 amps of discharge capability per cell, like the others, but these are less than half of the amp hour rating, which means your continuous discharge on these is like a 2.5 C. I could build a 2P55S pack out of these as well and still get close to 30 kilowatts, in terms of my overall range, but I'd be real comfortable in terms of my acceleration, because 150 amp hours at about a 2.5P would give me a continuous discharge of about 300 amps and likely a discharge, a 3-minute discharge of over 500 amps. So that would give me of around 600 amps. That would give me the acceleration I'm looking for, but it would be a little less of a battery pack at 150 amp hours. Well, if I wanted to add another string, I'd buy another 55 of them, and you get the idea, then the cost goes up. Okay, so up till this point, I gave you 2 examples of some batteries that I shop for on batteryhookup.com and how I can make them work for this car and what kind of specs that I'm looking for. I wanted to give you a bunch of more examples from some of those other vendors, but I didn't want this video to go 3 hours long. So I'm going to give you one final example of a battery that I shop for, and that is this one, like I mentioned, that I did buy, and this is what's going to go into the bus. So what I ended up getting, like I mentioned, was this big beast of a module here, and where I got this from was greentechauto.com. And here's the page that it's on. Apparently they're still for sale as of this date. Now these were built by a company called A123 Systems that was based in the US. A123 Systems was known for making high quality lithium cells, and if I remember correctly, they made them for some small OEM electric car manufacturers like Fisker Karma, I believe maybe for some OEM hybrid batteries, as well as I believe they made tool batteries, like high discharge batteries for like DeWalt tools and things like that. We talked about all the things that I'm looking for, right, for range and for acceleration and all that. So if we look at the web page on GreenTech Auto, we'll see that these have a lot of pros and one major con. And the major con is the voltage of these. These are already arranged, like I mentioned before, in a 26S 3P pack. They're made with their good high quality pouch cells that are 20 amp hours at 3.2 volts. But they're arranged in a 3P configuration, so it's 60 amp hours and then 26S. So it's 85 volts at 60 amp hours, which makes it a 5 kilowatt pack. Now, the problem with this is the voltage, right? Because I'm doing a relatively low voltage system, if your math is good, you'll understand that 85.8 volts per module means I can only do 2 of these to make a pack. That is an issue. I will have to parallelize these. There's no way to get around it. So that's the biggest drawback. So here's the good news about them. Let's start with the price, because that was the biggest driver of me making the accommodation of having to do these in parallel packs. The price on these is $275 for one, or $1,800 for a pallet of 8. And what I did was I bought a pallet of 8. Now I'm only going to use 6 of them, but if you do the math, it would have been $150 cheaper to get 6 of them, and it made sense to spend the little extra to get the full pallet of 8 and have 2 extras to use as backups. The other big advantage of these is they're obviously high quality A123 pouch cells, but they're also brand new. They've never been cycled. They're a couple years old, but they've never been used. If I were to buy like the Tesla Model S modules, or the other one I was looking at was a similar voltage Hyundai Ioniq batteries as well, or modules as well, those gave me the advantage of buying just like 6 or 7 of them to reach my voltage with the same amount of kilowatt hours and high current output and all that stuff. But the difference there was that if you look like even at GreenTech Auto, they sell those newer replacement Model S modules for $1,400. Multiply that by 6 and we're talking about $8,000. I mean, the cost here under $2,000 was just unbelievable. So they're cheap, they're brand new, they've never been used, they were charged really well, so I think they'll be easy to make parallel. The other thing about these is, look at the specs they have down here. Peak discharge current, 1,000 amps. Nominal discharge current, 600 amps. Peak charge current, 300 amps. They use a little bit different language than some of the other vendors, but my guess is that peak discharge current is probably the 10 second, and the nominal is probably the continuous. But look at that. Per module, on a 60 amp hour module, that has a 10C continuous discharge rating. That is unbelievable. Most other, especially the Chinese manufacturers that I was looking at, can't even touch that. And then also the peak charge current is 5C. That's why I think that I could probably overcome some of the limitations of high voltage paralleling. There's a couple other minor advantages on buying these as well. Not only are these new, they also have a 6-month replacement warranty from Green Tech Auto. You're not going to get that on used Model S cells that you buy at, on eBay or something like that. So they're tested and they're warranted at least for 6 months, which gives me time to find anything bad and return it. Other thing is, Green Tech Auto has locations in almost every major city around the US. They happen to have a location in the Chicago area, which is only a 30-minute drive from my house. So not only were these easy to pick up, but they're also going to be easy and locally sourced so I can return them. Okay, so now let's talk about how I'm going to configure these. Well, there really isn't much to talk about because, as you can imagine, the voltage of these things make it very limited in how I can configure them. If I put two together in series, that's 171.5 volts. Let's just call it 172. That's my voltage right there. I'm done. 2 in a series string is all I can do. Well, if I wanted to keep it to a single series string, I'd be limited to 10 kilowatts or about 25 miles of range. So that's not going to work. I'm forced to parallel these things. Well, like I mentioned before, the best way to parallel is to start your small voltage cells and parallel those first. Well, the problem here is I don't even have that. It's 85 volts per module. They're high voltage regardless. So I could have done the parallel first, like 3P, 2S, but it just made sense in the end just to do a clean 2S, 3P pack. So, which means creating 3 independent 172 volt packs and then parallelizing those. Now, obviously, I explained before, the downside is when you parallel high voltage, if there's any imbalance in these modules, it'll make eddy currents between the higher voltage modules and the lower voltage modules. Those eddy currents could be tens of amps if you're off by even 1/10 of a volt. So what I'm going to do is I'm going to do 3 independent packs, and then in each of those packs is going to have its own contactor and fuse. So when the contactors are off, the packs are disconnected. When the contactor closes, that's when the packs join together, and there could be eddy currents at that point. But I'm only going to join them together when the car is either turned on or when the charging's turned on. Now, going back to another advantage that I almost forgot to mention was savings in the BMS. When I did some research on these, I found that there's a manufacturer called Thunderstruck Motors, and I'll have their website in the video link with the others. They're an EV reseller, and they make some of their own stuff. And one of the things they make is their own BMS. Well, like I mentioned, a BMS is split between 2 different systems, a master control unit and measuring and balancing boards or units to balance the units themselves, which talk to the master unit. These are already outfitted not only in a casing, but they have a measuring and balancing board on each end. Each of these measuring and balancing boards take care of half of the cell groups in there. And they also have a 10-pin connector on either side. Well, the Thunderstruck designed their MCU to work with not only their measuring and balancing boards, but the A123 system measuring and balancing boards. So I didn't have to buy any measuring and balancing boards. They're already here. All I have to do is wire these 10-pin connectors up to this thing, and we have our whole BMS taken care of. So that right there probably saved me another $500. Well, so to summarize, we're going with these modules. They have the big drawback of me having to put a little extra work into the parallelizing and about an extra $250 of expense for buying extra contactors and fuses. But we have so much upside on these things. We have a big savings of about $400 to $500 on not having to buy measuring and balancing boards for our BMS. And we have a huge savings of a couple $1,000s over all those other options that I mentioned before. So cost was the big driver, but I think these things are going to work out well. In the next video, I'm going to show you how I'm going to build the battery box, which is going to be able to house these 6 modules in the back of the cargo area of the Volkswagen Bus. So make sure you subscribe and get notified of my next video, and you can see all the exciting stuff that's coming up. Thanks, I'll talk to you later.